Hello everyone and welcome back to another video. I think this is probably one of the most important videos I've ever made. In this video I covered moles, molecular and empirical formula. We discussed titration, percentage yield and so much more. Everything is in detail, and especially for someone who does not understand moles, everything is in easy words, easy terms, and I have made sure that I included a lot of examples. I hope this video helps you, and let's get started. Alright, let's start with moles. So before describing what moles is, I want you to think of this analogy. For example, if you have a tray of 12 eggs, 4, 5, 6, 7, 8, 9, 10, 11, 12. Instead of referring to it as 12 eggs, we say this is 1 dozen, right? We have created a term that makes it smaller, like that makes it easier to communicate. So instead of saying 12 eggs, instead of saying 24 eggs, 48 eggs, we just say 1 dozen, 2 dozen. So we have found a short form. Just as the same way, let's say if we have moles. So moles are extremely small, right? And it's so inconvenient to say that 6 trillion moles of oxygen reacted with carbon, right? That's so inconvenient. So we have created another term which is known as moles. Now, just as in 1 dozen there are 12 eggs, in 1 mole there are 6.02 times 10 power 23 particles. Okay, could be anything, could be atoms, could be ions, could be molecules. So for example, carbon. If we have carbon atoms, how many carbon atoms? As many as 6.02 times 10 power 23. When we have 6.02 times 10 power 23 carbon atoms, we can say we have 1 mole of carbon. Oxygen molecules, they would be like this. Oxygen exists as O2. So if there are 6.02 times 10 power 23 oxygen molecules here this time, we say this is 1 mole of oxygen. This could even be ion, any kind of ion, both metallic or non-metallic. Now, what is 1 mole? Mole is the unit of amount of a substance. Now that substance could be an atom, could be an ion or molecule, and that 1 mole contains 6.0 times 10 power 23 particles, atoms, ions or molecules. This number is the Avogadro's constant. Okay, so this number 6.02 times 10 power 23 is called as Avogadro's constant. That is how you can define mole according to the syllabus. Now what about AR? What is AR? AR is the relative atomic mass, is the average mass of isotopes of an element compared to 1/12 of the mass of an atom of C12. Let's look at it in detail. Do you know these masses which are given here? For example, 12 for carbon, 14 for nitrogen. This is basically the average atomic mass of one atom. In nature, there are isotopes, right? So for example, chlorine, there are 2 types of isotope, let's say Cl1735 and Cl17 and 37. So let's say this is the 2 types of chlorine isotopes that are present in nature. Now what about the percentage abundance? This exists as 75%, while this exists as 25%. This is percentage abundance. We can be asked to calculate the AR. What is AR? This one, average mass of isotopes of an element. So how do we do that? We just simply multiply the mass by the percentage abundance and divide by 100. So 35 times 75 plus 37 times 25 divided by 100. This equals to 35.5 grams. Now you will see this number is the same as the number mentioned in the periodic table for chlorine, 35.45, which which adds up to 35.5. So this is the AR. Now what about MR? MR is the same thing, but here we'll talk about molecules. Relative molecular mass is the sum of the relative atomic mass. So a molecule is made up of different atoms, right? So we basically just add the atomic masses of each of the atoms present in the molecule. Relative formula MR will be used for ionic compounds. Let's look at an example. Let's say calculate MR of water. So what is the AR of hydrogen? Hydrogen is 1.008, so we'll say it's 1. It would be 1 times 2 plus, what about oxygen? Oxygen is 15.999, so we'll say 16. It's better to use the exact same number given in your periodic table. Plus 16. The answer is 18 grams. What this means is 1 mole of water has a mass of 18 grams. Hope that makes sense. Okay, now calculate the MR of, this was water, calculate the MR of NH3. So you can look at the periodic table and you will know it's going to be 14 plus 3 into 1. This is going to be 17 grams. So this is the MR, and that's how you can calculate. Now in the past papers or in the question exam, you will be asked to calculate moles. And to calculate moles, we have 3 formulas. Let's look at the first one and the example. The formula is number of moles equals to mass divided by MR. MR is the molecular mass, or AR if it's an atom. This is given in the periodic table. All right. Now let's look at some examples. First, find the moles of 2 grams of neon atom. So what is the formula? Moles equals mass divided by MR. So we'll say 2 divided by MR of neon atom. This is 20. You can see it from the periodic table, and it's going to be 0.1 mole. What this means is that if we have 2 grams of neon atoms, we have 0.1 moles of neon. This is 0.1 mole. But what if they ask you to calculate number of neon atoms? So we know how many moles we have. We have 0.1 mole. And we know in 1 mole, we have 6.02 times 10 power 23 atoms. So in if we do the ratio method, in 0.1 mole, how many atoms will we have? We just need to cross multiply and we'll get. So number of neon atoms, 0.1 times 6.02 times 10 power 23. And that is 0.602 times 10 power 23 neon atoms in 2 grams. So using this formula, you can calculate the number of moles. You can even calculate the mass of substance. When you multiply moles times MR, that is going to be the mass, and you can even find MR. You just have to move the equation. Now first we calculate the number of moles. Now there's another equation to calculate the number of moles. Now remember, this equation is specifically for solutions only. Formula equals to volume of the solution, but make sure it is in liters, okay? Multiplied by concentration. Concentration, it's also going to be in moles per liter. Now, what is the meaning of concentration? I mean, for example, if we say 2 moles per liter, that means if we have 1 liter of solution, we'll have 2 moles of whatever the solution that there is. This is what concentration means. Okay, now let's look at some conversion factors that you need to be aware of. Now we said volume should be in liters, right? But sometimes they will give it to you in decimeter cube. Remember, 1 liter equals to 1 decimeter cube. They're both same. But what if they give it to you in centimeter cube? Then you need to know that 1 liter equals to 1000 centimeter cube. Oftentimes you will be asked to convert them. Let's look at one example. Okay, so what is our formula? Formula is volume times concentration. Moles is going to be volume 250. Make sure to divide by 1000 to convert this into decimeter cube or liters, multiplied by 2 to 0.5 moles. Again, if you want to find the number of sodium hydroxide molecules, you just multiply this with 6.02 times 10 power 23. Okay, now using this formula, just like the previous one, you can find even the volume if you have moles and concentration, or you can also find the concentration if volume and moles is given. In some cases, if you can even equate both of them to find an unknown value. Now we'll do another example. So the question is find the concentration, right? What is the formula of concentration? Concentration equals to moles divided by volume. Moles divided by volume. The volume here is known. The volume is 5 liter, but the moles are unknown because we only have the mass. So we'll have to find the moles, but we can substitute volume here. We have the grams, and based on our previous equation, we know that moles equals to mass over mr. What is the mass? Mass is 8 grams. What is the mr? Mr is 23 plus 16 plus 1. This is going to be 8 divided by 40, which is 0.2 mole. Right? 0.2 divided by 5 liters, and you get 0.04 moles per liter. We have another example. Calculate the mass of copper sulfate, CuSO4, which needs to be used to prepare 500 centimeter cube of, remember this is the volume, centimeter cube, and of 0.1 mole decimeter cube solution. This is the concentration. So what is the question? Question asks you to find the mass. Remember the two formulas. So according to the first equation, mass is going to be moles times mr. The moles is unknown, but what is the mr? 64 plus 32 plus we have 4 oxygen, so 4 into 16 is going to be 160. So we know the mr is 160. Now we need to find the moles. So we go to the second equation. It says that moles equals to concentration times volume. Concentration is 0.1 multiplied by volume. Remember, volume has to be in decimeter cube. So it's going to be 500 divided by 1000. The answer would be 0.05 moles. So now you do have the moles, and this mole can be equated in the first equation. 0.05 times 160 is going to be 8 grams. So in order to prepare a 500 centimeter cube of 0.1 mole decimeter cube solution, you need 8 grams of copper sulfate. Now we will look at the third formula to calculate moles, and that is number of moles equals to volume in liters divided by 24 liters. Okay, 24 liters is because that, for example, if we have 1 mole of gas, this formula is for gases. Remember the previous one was for solution, concentration times volume. This one is for gases. 1 mole of gas at room temperature and pressure, RTP, this occupies a volume of 24 liters. 1 mole of any gas at room temperature and pressure occupies a volume of 24 liters. Remember, this is also known as molar volume, which is the 1 mole of gas at room temperature and pressure occupies 24 liters. For example, can you do this? Moles is going to be volume 240 divided by mr. This is 24. The answer is 10. So these are the 3 equations that we have studied to calculate the number of moles. Alright, so now we're going to discuss about molecular and empirical formula. Before going on the explanation, this is what the syllabus has told us about both of these formula. Molecular formula is a compound of a compound is the number and type of different atoms in one molecule. So in simpler words, if we will have to write it, we can say molecular formula says the exact composition of a compound. For example, if we want to look at the example of glucose, is C6H12O6. This is the molecular formula. It tells us that in one glucose molecule, we have 6 carbon atoms, 12 hydrogen, and 6 oxygen atoms. Whereas, if we look at the empirical formula of a compound, this is the simplest whole number ratio of different atoms or ions present in the compound. So basically, it is the simplest form of a molecular formula. Then, how do we find the empirical formula? So we can say we can divide this by 6, and we'll have C1H2O1. Do you see? This is the empirical formula. We cannot divide this further. Let's look at another example. For example, benzene. What is the molecular formula? C6H6. Again, we can divide by 6, and the empirical formula would be CH. I'll give you another example of oxalic acid. Can you try to do this one? What do? You just divide by 2, and the empirical formula would be HCO2. Alright, to learn how to find the empirical formula. So the question is, find the empirical formula of a compound that has 25.4 gram of copper and 3.2 gram of oxygen. So what you're supposed to do is you're supposed to find the moles of copper and oxygen first. Okay, so you have copper and you have oxygen. Remember, moles equals to mass over mR. So this is going to be 25.4 divided by 64, and oxygen would be 3.2 divided by 16. So the ratio between them is 0.4 to 0.2. We can simplify this. Multiply by 10. We get 4 into 2, and then we can divide by 2 to get 2 to 1. This shows us the empirical formula is Cu2O. This is the empirical formula. Now I have another question. I want you to solve it. Pause for a minute and try to solve it. So calculate the empirical formula of a compound of phosphorus oxide that's mass is 1.10 grams when the mass of phosphorus is 0.62 grams. So phosphorus oxide, let's write the ratio. It's supposed to be phosphorus and oxygen. Now they have given us the mass of phosphorus, but they didn't give us the mass of oxygen. So to calculate the mass of oxygen, we can just subtract it. 1.10 minus 0.62 is the mass of oxygen. This is going to be 0.48. 0.48. Divide both of them by their MR. The ratio is 1 to 1.5. Now we just have to simplify it. Let's multiply these by 2, and we get 2 into 3. So the empirical formula is going to be P2O3. Alright, now we have another example. Can you try to do this first? A compound having the following percentage composition by mass, where we have 80% carbon and 20% hydrogen. Empirical formula, we need to find the moles, but the mass is not given. Percentage is given, so we just divide by percentage. Simple as that. This is going to be 80 divided by 12, whereas hydrogen is going to be 20 divided by 1. Now if you divide both of them by 6.67, you get 3 to 1. So the empirical formula is C3H. This is just not a real empirical formula. This was just a sample example. Alright, so now we calculated the empirical formulas using the ratios, but this is not the molecular formula. But based on the empirical formula, we are able to convert this into molecular formula. But we need to know another equation where N equals to molecular mass divided by empirical formula mass. And what does N mean here? N is the multiplier. You will understand this term when you see the example. Okay, let's say that our empirical formula is, for example, CHO2. CHO2. This is our empirical formula. And they told us that the molecular mass is 90 grams. And you need to find the molecular formula, that means the exact ratio or the real ratio of the compound. So what you do is, so molecular mass is 90. This is the mass of the original molecule divided by the mass of empirical formula. So this is going to be 12 plus hydrogen is 1 plus 2 into 16. The answer is going to be 2. This is going to be 2 times the empirical formula. So we multiply CHO2 times 2. We get C2 H2O4. This is our molecular formula. So going up, we calculated these empirical formulas. If we knew the molecular masses, we could have calculated the molecular formulas as well. Alright, so now I have a practice question. So one of the ores of copper is mineral chalcopyrite. A laboratory analysis of a sample showed that 15.15 gram of chalcopyrite has the following composition by mass: copper 5.27 grams, iron 4.61 grams, and sulfur is the only other element present. Relative molecular mass is 150 grams. Find the empirical formula of chalcopyrite. Alright, so mole is mass over mr. The mass of copper is 5.27 divided by mr is, or ar here, is 64. Iron is 4.61 divided by 56. Remember, we got these values 64 and 56 from the periodic table. And sulfur, they didn't mention the mass of sulfur, but we can calculate it. 5.27 plus 4.61 plus x equals to 15.15. If you don't understand how, because copper plus iron plus sulfur equals to 15.15, right? So we know copper, we know iron, we can find sulfur. That is going to be 5.27 grams. If we calculate it, now if you just divide them by 0.08, so our empirical formula will be Cu1, Fe1, and S2. Now we can find the molecular mass. I just changed the value of relative molecular mass to 400 because this is just like a random number and this was giving us better answer, so I just changed this to 400. The steps are same. The multiplier N is going to be the relative molecular mass divided by empirical formula mass. So this is going to be 400 divided by the empirical formula mass. So we have 1 copper, 64, plus Fe, iron is 56, plus we have S2, 2 of sulfur, so 2 into 32. Now if we multiply 2 with our empirical formula, it would give us Cu2, Fe2, S4. Just note that this is not the real molecular formula, this is just based on our calculation. Now there's another example. Please try to do this first. 0.8 grams of solid sodium hydroxide is dissolved in distilled water to a final volume of 1 decimeter cube. Find the concentration of solution. Now you don't have to calculate any formulas here, just concentration. This is kind of a revision of the previous chapter. So concentration is moles divided by volume. Volume is 1 decimeter cube, but moles is unknown. So moles is also equals to mass over mr. Mass is 0.8 divided by mr. So 0.8 divided by 40, 0.02 moles. We can use this mole here, 0.02. So we get concentration of 0.02 moles per decimeter cube. Now the second part is, how many liters would have 1 mole of NaOH? Can you do this first? Okay, so if we know the concentration, according to the concentration, we can know that in 1 liter, we have 0.02 moles, right? This is the meaning of concentration. 1 liter has 0.02 moles. So if we want 1 moles, how many liters would that be? X. Just I'll remove the units here to make it simpler. So this is just going to be 0.02 x equals to 1, and we get 50. So we need 50 liters of this NaOH solution to have 1 mole of NaOH. Alright, now we will study another concept, which is percentage composition by mass. I will try to illustrate this first. Let's say we have a molecule of beryllium oxide, okay? So let's say this is beryllium oxide. What is the mass of beryllium? The mass of beryllium is 9 grams. What is the mass of oxygen? 16 grams. So if we want to find the percentage of beryllium, what we have to do is we divide 9 divided by 9 plus 16 percentage. So multiply this by 100 and we get 36%. So that means in this 36% is beryllium. The rest of this in this molecule is 100 minus 36, going to be 64. So in beryllium oxide, 36% of mass is by beryllium and 64% of mass is by oxygen. Just notice that to find percentage composition by mass of oxygen, either we can subtract 100 minus 36 because we know total is 100 and 36 is by beryllium, so the rest is 100 minus 36, or we can use the same formula as we did here. What is the mass of oxygen? This is 16 divided by the total mass, we get 64. So we can say that the percentage composition by mass formula is mass of the element divided by total mass of the molecule. Now we'll do some examples. Can you try to do these examples first? Calculate percentage by mass of iron in iron 3 oxide. So what is the formula of iron 3 oxide? This is going to be Fe2O3. Okay, how do we know that? Because iron is, they're saying iron is Fe plus 3. This is stoichiometry. Oxygen is minus 2. So to write the formula, we just bring this here and bring that here. It would be Fe2O3, and that's how we obtain the formula of iron 3 oxide. 70%. Water in copper sulfate 5 water. So copper sulfate 5 water, that means we have 5 water molecules dot 5 H2O. What about copper sulfate? So copper is Cu plus 2 and sulfate is SO4 minus 2. Both of them come here. Cu2 SO4 2, we cancel them, no need to write this. So Cu SO4, let's write this as Cu SO4 dot 5H2. So percentage of water, what is the mass of water? It's 1 plus 1 plus 16, this is 18. So we have 18 times 5 because there are 5 divided by copper sulfate plus 18 into 5 because also water is included, total mass. Multiply this by 100 and you get 36%. So we just studied what is percentage composition by mass, the formula, which is mass of the element for which you're trying to find the percentage composition divided by the total mass of the substance. Now we'll study another concept, which is percentage yield. Now percentage yield is how much you are obtaining from the reaction, and then percentage yield would be the actual yield divided by the theoretical yield. For example, if we say that A reacts with B to give us C, let's say we did some calculations and we found out that when 1 mole react, let's say 1 mole and 3 moles react to give us 7 moles of C. This is not addition, we do ratio method and calculation based on each individual formula. Let's say we get 7 moles, but that's only in calculation. When we do it in the lab, we don't get 7. For example, we get 6.5 moles. So this is known as theoretical yield, which is found after calculation, while actual yield is found after doing the experiment in the lab. Now, why is actual less? This is because maybe some of B didn't react. Maybe some of B was lost during reaction, or whatever the reason. Not all of it reacts. So to calculate the percentage yield, we'll do 6.5 divided by 7 times 100. Percentage purity basically means mass of pure substance divided by mass of impure substance multiplied by 100. For example, if we talk about iron ore, let's say if it has Fe2O3 and there's an ore of it, but the ore doesn't just contains iron oxide. Let's say it has some dirt, let's say it has some other rocks, so that increases the total mass of impure substance. For example, the iron oxide here has the mass of 2 grams, but the total mass is 6 grams. It has a lot of dirt. So 2 divided by 6 multiplied by 100. This is our percentage purity. This helps us to find out how pure it is. If this was 2 grams for iron oxide and total mass was also 2 grams, we would get 100% purity. And these are 3 important concepts we just studied. If you want, you can take a screenshot. Okay, now we'll study a very important concept in moles that is going to be repeated over and over in a lot of aspects. Titration, limiting reagent, and finding the maximum yield. So first of all, what is titration? Now, a titration is when you basically react acid and base. If, for example, if you know the concentration of base, you can find the concentration of acid. Let's see what's going on here. So basically, we have a beaker. First of all, there's a beaker. Let's say that beaker has 25 centimeter cube of sodium hydroxide solution in the beaker, and let's say its concentration is 0.1 moles per liter. So we can say this is a standard solution of sodium hydroxide. What is a standard solution? Standard solution is basically a solution of known concentration. Then in our burette, what do we have? Acid. We have hydrochloric acid, but the concentration is unknown. We don't know the concentration, and the question is find the concentration of hydrochloric acid. Now what happens is over here the burette is open, and drop by drop it reacts. Let's say that 18.5 centimeter cube of acid reacted with 25 centimeter cube of sodium hydroxide. That means when this much reacted, it neutralized. How do we know it neutralized? Maybe there's a universal indicator there. Maybe there's an indicator there that shows us that okay, now this NaOH has neutralized. The question is find the concentration of hydrochloric acid. Now we have to follow certain steps, and this is very easy, but this is a very important concept. First step that we have to do is we have to write the equation. First, let's find the moles. Based on all the information that we have, we can only find the moles of sodium hydroxide. This is going to be 0.1 moles per liter multiplied by 25. Remember, this is centimeter cube. Convert this into liters or decimeter cube. Divide by 1000, and we get 0.0025 moles. Okay, now we have to find the concentration of HCl. The formula for concentration is moles divided by volume. We don't know the moles, but we do know the volume, which is 18.5. 18.5 divided by 1000. We don't know the moles, but we know the moles of NaOH. So we know do this important concept of finding the ratio. So we can say one hydrochloric acid reacts with one NaOH. So the ratio between HCl and NaOH is 1:1. So what is the moles of NaOH? Is 0.0025. So the moles of HCl, find X, multiply it, and you get 0.0025 as well. It's the same moles. So the moles of hydrochloric acid is also 0.0025. It is going to be 0.135 moles per liter. Now, there's another example of titration. Please pause the video and try to solve it. This is we just follow the same steps as before. Okay, now let's try to do this together. So they're saying 24.2 centimeter cube of solution containing 0.2 mole per liter of HCl just neutralized 25 centimeter cube of KOH solution. What is the concentration of KOH solution? So let's first identify what do we have. So we have hydrochloric acid, and in hydrochloric acid we know the concentration. The concentration is 0.2 mole per liter, and we also know the volume. The volume is 24.2 centimeter cube. What about potassium hydroxide? The concentration is unknown, but the volume is 25 centimeter cube. First step is write down the equation of both of them, hydrochloric acid and potassium hydroxide. They react to give us potassium chloride, KCl plus water. Okay, now we're supposed to find the moles of hydrochloric acid. So moles of hydrochloric acid is going to be concentration times volume, 0.00484 moles. Now we know the moles of HCl. We can find the moles of KOH. What is the ratio between hydrochloric acid and KOH? It is 1:1. So 1:1. If the ratio was 2, for example, if there was 2 written here, we will write 2. If, for example, this was 3, we'll write this as 3:2. The ratio depends on the number that's written before the molecule, but here it's 1:1. I hope that makes it clear. 1:1. So they're both equal. So moles of hydrochloric acid equals to moles of potassium hydroxide. Now we know the moles of potassium hydroxide. We know the volume. Can we find the concentration? Yes. Concentration of potassium hydroxide equals to moles 0.00484 divided by volume in liters, which is going to be 25 divided by 1000, which gives us 0.194 moles per liter. Okay, we have one more example. This is not titration, but this involves moles. A compound contains only aluminum and carbon. So 0.03 moles of this compound reacts with excess water to form 0.12 moles of AlOH3 and 0.19 moles of CH4 methane. Write a balanced equation. Alright, so they told us there is a compound which contains aluminum and carbon only. Now, we don't know the empirical formula, we don't know the molecular formula. We just know that we don't know how many aluminum and carbon atoms are present. We just know that it has aluminum carbon, and 0.03 moles react. 0.03 moles of aluminum compound reacts with excess water. So we have a lot of water. This reacts to give us 0.12 moles of LOH3, 0.9 moles CH4. So what we do here, we're supposed to divide the second one, these two, like the products, by the smallest number here 0.03. We get 4. So we know this is 4AlOH3. The reason why we're not dividing these is because we don't know the formula. And also we know that water is in excess. So we're just dividing the product now. 4AlOH3, 3CH4. So if we want to balance it, we know we have 4 aluminum. So this is going to be Al4. How much carbon we have? We have here 4 aluminum and 3 carbon. So we have Al4C3 plus water. How many hydrogen we have? We have 3 times 4 is 12. 12 hydrogen. From aluminum OH3 and from methane we have 12. 12 plus 12, that means we have a total of 24 hydrogen atoms. We'll write 12 H2O and oxygen. Count the oxygen. Oxygen is 12. So that makes it balanced. And then we will write the same. So this is our balanced equation. Okay, now we'll discuss what is a limiting reagent. Now, as the name suggests, this is the reagent that is in limited quantity. When in a reaction, it gets completely used up. So you might be asked to identify the limiting reagent in a reaction. Say we have 0.07 moles of silicon and they react with 25 grams of bromine. So the first step is we have to write a balanced equation. Silicon plus, remember bromine is always 2, it's a diatomic, SiBr4. So we need 2 of them here. We wrote down our balanced equation. Now we know that in the experiment, moles of silicon that reacted is 0.07 moles. Now the next step is find the moles of bromine. So moles of bromine is going to be mass divided by mR. Mass is 25 grams divided by 2 into 80. This gives us 0.15625 moles. Now let's say if this many moles reacted, how much silicon would we get? Okay, what is the ratio between silicon and bromine? So it is 1 to 2. 1 silicon mole reacts with 2 bromine. So 15625 x. What is the moles that reacted with this much bromine? Is going to be 0.078 moles. So now you can see that silicon was the limiting reagent because 0.07 is less than 0.078 moles. When all the bromine, all this 0.156 mole, when all of the bromine reacted, we got more silicon. So silicon is a limiting reagent. Okay, now we'll talk about maximum yield. Maximum yield is basically the maximum amount or maximum mass of a substance. So we'll study this using an example. 6 grams of cobalt carbonate was added to 40 centimeter cube of HCl with HCl. And this had a concentration of 2 moles per decimeter cube. Calculate the maximum yield or mass of cobalt 2 chloride 6 water. The maximum yield is going to be moles times mass. Mass here would be mR. mR times the number of moles of COCl2.6 water molecules. Okay, so what is the mass or mR? That is going to be, you just have to add the AR from the periodic table, 238. But what about the moles? Let's find the moles. Let's see what values are given to us first. So this is for cobalt carbonate. We know we have 6 grams. For hydrochloric acid, we know we have 40 centimeter cube and we have 2 mole per decimeter cube. So we can find the moles of hydrochloric acid, basically the moles of hydrochloric acid, and then using the ratio method we can find the moles of COCl2. So what is mole of HCl? This is going to be 40 divided by 1000 multiplied by 2. This is the concentration. 0.08. Now we know the moles of HCl, and we can do that to find COCl2. Using the moles of COCl2, we can find the moles of COCl2.6 water. This is what we need. COCl2 is in the ratio of 2 react with 1, okay? To 1. So if moles of hydrochloric acid 0.08, but with the mole, X is going to be 0.08 divided by 2. This is 0.04 moles. Now, what is the ratio? The ratio is 1 to 1, okay? So this is going to be 1 to 1. If this is 0.04, this is also 0.04 moles. Now, coming back to our maximum yield, we can say it's going to be 0.04, gives us 9.52 grams. So this is the maximum amount of hydrated copper cobalt which we'll get. Show that a cobalt carbonate is in excess. We basically reacted cobalt carbonate and hydrochloric acid. Let's write the ratio between them, which is 1 to 2. 1 to 2. Now, based on the information given, we know that the moles of hydrochloric acid was 0.08. So, mole of hydrochloric acid that reacted is 0.08. So in our reaction, it was 0.08 mole that reacted. But let's see what would happen if all the cobalt carbonate had reacted. What is the moles of cobalt carbonate? Mass divided by mR. The mass is given, which is 6. So 6 divided by mR, 0.05 moles. So let's see if all the cobalt carbonate had reacted, it would be 0.05. Multiply it by 2, 0.1 moles. So you can see cobalt carbonate is in excess, because if all the cobalt carbonate react, we would get 0.1 mole. But we only had 0.08 moles of hydrochloric acid that reacted.